Hello, welcome to this video on functions. So we are going to look at what a function is mathematically, and we are going to encounter some basic functions that will appear later in calculus and will come back frequently. So let's have a little outlook of what we will cover in this video. So first of all, the definition of a function. What is a function mathematically speaking? Then some examples, some basic functions like polynomials, y equals x squared, for instance. Rational functions, that's a polynomial divided by another polynomial. And root functions, for instance, square root of x. And then I will say a little bit about finding the zeros of functions. So zeros of functions are those x values for which the function equals 0. If you would graph the function, it is where it crosses the horizontal axis. And I'll wrap up with a summary of what we have seen. So let's get to it. Very generally speaking, a function is basically a relationship, a rule. So we take here very generally, we take a set A and we take a set B, and then if we pick an element x in this set A, so I've drawn that here, we pick an x in the set A, and then we assign exactly one y from the set B to that. Now this is very abstract and very general. So in general, we will have something like y equals x squared. So we pick a number and we assign a kind of formula to compute another number, and that is the y value. It can be more general, and sometimes it helps to think of it in a more general context. For instance, say that our set A here on the left are all the students that are currently following this course calculus. What I could do is, for each of you, I could assign to you your age, so how many years old you are. That can be 18 or 19 or 20 years old, for instance. And what you already see there is that if I take a student and I assign the student's age to it, that many of the students will be mapped to 18 or 19 years old. So for every student, there is precisely one y value. For every x is a student, there is exactly one y. But many different students are being mapped to the same number, 18 or 19. Another function you could think of, for my collection A here on the left, I'm still going to take students that are doing the calculus course. But now what I'm going to assign to you, to each of you, is your mobile telephone number. And as you know, mobile telephone numbers are unique. For every student, there is precisely one telephone number. So what that means is that we have a one-to-one mapping, student to telephone number. And I could also go back. If I have the telephone number, I could go back and see which student belongs to that. So sometimes functions are special in the sense that there is also only one y value. But very often that will not be true. So for instance, a function that you know very well is a parabola, say. So y equals x squared. And you know that if you draw this, so horizontal x is x, vertical x is y, you get a parabola, right? This is nothing special, you've already seen that in high school. So that goes approximately like this. So this is y equals x squared. So what you see now is that if I pick some x value, that there is for this x precisely one y value. So for every x, there is only one y. However, if I would pick a y value, say here this value, and I would draw a horizontal line here, you see that there are two x values being mapped to that y value. So here is a crossing and here we find an x value, and here is a crossing and here is another x value. So the mapping from x to y needs to be unique, not the other way around. So hopefully that makes the concept of function a little bit clear what it means mathematically. So it's a rule, you take one x and you assign precisely one y to it. So that is the basic definition of a function. And later on we will do many things with functions, but this is how you can think of it. And of course very often we will have functions f that will go from the real numbers to the real numbers, or maybe a subset of the real numbers. But that's what we deal with most often, but it does not have to be like that. So A can also be the set of students. Okay. Now we have a few more definitions here. So this set A, that consists basically of all the x values together, is called the domain of the function. And very often we will take that, when we work with numbers, as the largest collection that it makes sense to apply a function to. So for instance, if you have the function f of x is the square root of x, well, you know that it only makes sense to take the square root of a non-negative number. So x needs to be larger or equal 0. So very often we will take as the domain for A, we will take the set from 0 to infinity. So the largest collection of numbers that it makes sense for the function that you can apply it to. And then there is one thing more here, Ra, and basically that's all the y values that are attained, that you reach with the function. So if you look here at what it says here, it says we pick x values and then we compute f of x and we put them all together in a set. So that's what this notation means. We take a set, that's the curly brackets, we have seen that notation before, and then we take all fx's for which x is in the collection A. And it can be a subset of B, so B can be bigger, and it can be that the function only reaches part of it. Let's look at a couple of examples to make that a little bit more clear. So, for instance, a very simple function. Let me grab a bit of paper here. So, let's see what this means. So, first example is a straight line, if you would draw the graph of the function. So, I'm going to consider the function f of x equals 2x plus 3. Now, if you would like to know what the domain is of this function, we are going to consider the largest of collection of numbers that we can apply it to. Well, we can apply this function f. So we can apply f to all x in R. So the domain that we labeled A is every real number. The range, probably you know what this graph looks like. It's just a straight line. Every y value can be attained. So the range of this function, Ra, is also every real number. For every y, we can find an x that is being mapped to this y value. Let's look at an example that is a little more interesting. I'm going to build up the examples in complexity. So we have seen in a previous video the absolute value of a function, and probably you recall what that looks like. It is basically the line y equals x for positive x values, y equals minus x for negative x values. So this is y equals absolute value of x. And you can see that you can apply it to every real number. So the domain A equals R, and the range R, A. Well, now we cannot get to every y value. So if you look at the y values that can be reached by the function, you see that it is 0 and every positive number. So this is 0 to infinity. For instance, for y equals -1, there simply is no x that is being mapped to that y value. And finally, one more example. Let's consider the function f of x is the square root of x plus 1 plus 2. So for which x values can you do this function? Can you put into this f? Which x values can you feed to f? Well, for it to make sense, we need a non-negative number under the square root. So the condition is for the domain, the condition is going to be that x plus 1 should be bigger or equal 0, which is the same. So this notation means is equivalent, is exactly the same as x is bigger equal -1. So the domain A is the set from -1 up to infinity, and -1 is included. And then the range well, you know that the square root of a number is always going to be bigger or equal 0. Then we have a +2 here in the formula. So if you compute an f value of some x, it is always going to be 2 or bigger than 2. If you would plug in x equals -1, then here you find 0 and the whole thing is 2. And as soon as you plug in a different x value, for which it still makes sense, so a different x from the domain, you get something that is bigger than 0. So the range here is going to be from 2 up to infinity. So that is the range of this function. So this was a very general definition of a function, domain, and range. Now let's look at some functions that we are going to be working with. So the simplest type of functions are the polynomials. And what are polynomials? Well, the definition is here, but first let's write a couple of them down. So if you have the function f of x equals 7, that is a polynomial. F of x equals 2x minus 3 is also a polynomial. F of x equals 2x squared minus 9. F of x is minus 3x to the power 10 plus x squared. So these are all polynomials. So basically what we have is possibly a constant, like the 7, the minus 3, and the minus 9 here. And then going from the right to the left, some constant times x, some constant times x squared, all the way to some constant to x to the power n minus 1. N is a natural number like 10, 100, or 1000, and a n x to the power n. So this is the highest power of x in the polynomial, and here it is x, here it is x squared, and here the highest power is x to the power 10. So those are all polynomials. The n, the highest power, is called the degree of the polynomial. So this polynomial has degree 0 because there is no x in there. X to the power 0 if you like, that's 1. This one has degree 1 because that is the highest power of x. And this one has degree 2 because x squared is the highest power of x. And this one has degree 10 because 10 is the highest power of x in the polynomial. So n is the degree of the polynomial. Then these numbers in front of the x's are called the coefficients. And here it says a(n) is unequal 0. So that is basically the highest power of x and the coefficient. So here it is 7, here it's 2, here it's 2, here it's minus 3. A bit on the name. I'm not sure if you've ever heard that before, but poly means many, And nomials, this is just terms. So these things are all terms in the polynomial. So it's terms that you add together. And you've got many of them. So polynomial is just many terms. That's what the name comes from. Let's see, do I want to say anything more about polynomials? So we'll meet them very frequently. And of course, you already know from high school mathematics, polynomials are great to work with in the sense that they have nice properties. For instance, they are defined for all x values, so you can always apply them. You can easily differentiate them. We haven't seen differentiation in this course yet, but we'll come to speak about it. And you can always easily find the derivative. Also, you can easily integrate them. So they are nice functions, and we will be using them in many applications. Let's go to the next category of functions, the rational function. So a rational function is some polynomial over another polynomial. For example, you could take the polynomial f of x equals x squared plus 7x minus 11 over x squared minus 4. So as you see, we have a polynomial over another polynomial. This is a rational function. Now, these are slightly more complicated than polynomials because you may have division by 0. So if you would like to find the domain, you have the requirement that x squared minus 4 should be unequal to 0. Otherwise you have division by 0. So that means that x plus 2 times x minus 2 should be unequal to 0. So what we find is that x cannot be minus 2 and x cannot be 2. So what we find for the domain is that the domain is every real number, except, that's what this notation means, that we throw out some of the elements, minus 2 and 2. So this is the domain. Every real number except for 2 and minus 2. So that's what this notation means, that you delete them from the set. Last type of functions that I would like to consider in this video are roots. And the simplest one is the square root function. So you already know that if you have y equals square root of x, that you get this graph, right? So we have x values, we have y values. You can only apply it to non-negative x's. The square root of 0 is 0, and then the function looks a little bit like this. Y equals square root of x. And it keeps increasing, right? So if you let x go to infinity, then square root of x will also go to infinity. And the formal definition is in the blue box here. So we pick a non-negative x value, and then y equals square root of x. That is the unique number such that if you square y, you find x. And for instance, the square root of 4, if you would only use this thing, well, both 2 and minus 2, if you square them, give 4. We only want one of them, so we are going to impose a requirement that y should be larger or equal 0. In particular, that means that we have this here. So if I write that out for an example, if you would take the square root of minus 2 squared, that is the square root, well, minus 2 times minus 2 equals 4, and that is 2, which is the absolute value of minus 2. So that's why we have an absolute value here, and then it always works. A bit more general. So here in this definition we have the square root, and that is basically the nth root of a number with n equals 2. So we can generalize this a little bit, and if we pick a natural number bigger equal 2, then the nth root of x is the number y, such that y to the power n equals x. And if this n here is even, then we require both x and y to be non-negative. So let's see what that means. That seems a bit very dry, but what it means is that if you take, for instance, the cubic root of 8, then we are looking for the number y such that y to the power 3 equals 8. And if you think a little bit about that, you will see that that equals 2. And if we take the cubic root, we can also do that for a negative number. And for minus 8, you find minus 2, because minus 2 times minus 2 times minus 2 equals minus 8. Then the quartic root of the fourth root of 16 is the number y such that y to the power 4 equals 16, and that is again 2. I pick easy numbers here. And the quartic root, the fourth root of minus 16, that's not defined. Because what we would need is a number y such that y to the power 4 equals 16. And we cannot do that, because if you have something to the power 4, that's always going to be a positive number. So we cannot get minus 16 there. So that's undefined. Okay. Now, with what we have here, we can already link a previous topic to what we have seen here now. Because, for instance, we could have the question, example, what is the domain of the function f of x equals square root x squared minus 4. So as we have seen, the argument of the square root, so the x squared minus 4 bit, should be non-negative. So we have the restriction now that x squared minus 4 should be larger equal 0. This is an inequality that we have studied before. So what do? Well, we write it as x plus 2, x minus 2 bigger equals 0, and we make a sign chart. So here below we put x, here above we put x plus 2, x minus 2. There are two special numbers, minus 2 and 2, where the expression equals 0. And we now know that on this interval, the expression is either positive or negative, but it doesn't change sign there. Similar in between minus 2 and plus 2, and also here it is either positive or negative. To find out the sign, let's say in this region, we pick x equals 1000, and then we get plus times plus equals plus. In this region, we could pick 0, because that's in between there, and then we have 2 times minus 2, that's negative. And left of minus 2, we pick minus 1000, we get minus times minus equals plus. So we can now read off that x should be less or equal minus 2, or x should be bigger equal 2. So the domain A equals minus infinity up to minus 2, and minus 2 is included, and then union 2 to infinity. So the elements can come either out of the left interval or out of the right interval, and we put them all together, and that's the domain of this function. One of the problems that we will be studying in what comes in the next videos is finding the zeros of a function. So what is the zero of a function? Well, it's this value that I labeled alpha in this graph. So a zero of a function, here there is only one, there can be many more. That is a value for which the function is zero. So where does the function cross the horizontal axis? Now sometimes that is an easy question to answer. For instance, if you have a straight line, f of x is ax plus b, well, you can simply find an expression for the zero. Also, if you have a parabola, you know that's still from high school, ax squared plus bx plus c, then you have this standard formula that you should know by heart. So there are two possible zeros, minus b plus or minus the square root of the discriminant. Discriminant is b squared minus 4ac divided by 2a. So here you can find a simple expression for that. It doesn't always work like that. And I will show you some numerical methods, not in this video, but later on. If you cannot easily compute the zeros, how you can still find them numerically, so a couple of digits. For polynomials, there is a very interesting theorem that says that a polynomial of degree n, so remember that's x to the power n, the highest power in the polynomial, it says that it has at most n zeros. And for n equals 2, you already know this to be true, because for instance, if you look at the function y equals x squared, you know that there is 1, 0. X equals 0 is a 0 of this function. Now if you simply add 1 to it, so I do y equals x squared plus 1, you see that there are no zeros. It doesn't cross the horizontal axis. And if you would subtract a number, so let's say that we look at this graph, so y equals x squared minus 1, and I could subtract basically any positive number, then you see that you have two intersections. So this one has 2 zeros. So here you see that if you have a parabola, quadratic function, that you either have 2 zeros, 1 zero, or no zeros. So indeed you have at most n distinct zeros. But it also means that you take x to the power 25 plus 3x to the power 20 minus 3x squared plus 10, some expression with x to the power 25 as the degree of the polynomial, the highest power of x, that there will be at most 25 zeros. No more, possibly less. And there is a bit more. You can also say, and this looks very abstract, and I'm going to give an example in a second. If you have a polynomial and you have found somehow a zero of that polynomial, that you can write this function f as x minus alpha times g of x, with g another polynomial of degree less. So you can basically factor out x minus alpha. So you can see that alpha is a zero of the function f here, because if you plug in x equals alpha, this becomes 0 and the whole thing becomes 0, times another polynomial, and that is special. So let's have a look what that means and look at some examples. So for instance, in blue example, f of x equals x to the power 3 minus 5x squared plus 6 times x. Now you can easily see that if you plug in x equals 0, the function is going to be 0. So I can write this as x minus 0. So I use basically the formula in the block times a new polynomial g of x, and here g of x is easy to see. It is going to be x squared minus 5 times x plus 6. And of course I do not need to write the minus 0 in that expression, so I can just write f of x is x times gx. And you see that this is again a polynomial. And of course, I can also write this thing as, what do we have? X minus 3, x minus 2. So apparently we can write the function f of x, the original function, as x times x minus 3 times x minus 2. And the nice thing about this factorization, this way of writing it, it's called a factorization, is that you can immediately tell for which x values the function is going to be 0. So x is 0, x equals 3, and x equals 2. Let's do one more example on a fresh bit of paper. So a little bit more difficult. F of x equals x to the power 3 plus x squared minus 4 times x minus 4. This one you can also write as a product of lower degree polynomials. It's maybe a bit more difficult to see, but what I can do is in the first two terms, so these two, I'm going to write them as x squared times x plus 1. And then the last two, I'm also going to pick them together, and I can pull out a minus 4. So minus 4 times x plus 1. And what you see now is that I have an x plus 1 and another x plus 1. So I can also take these two together, and I can write this as x squared minus 4 times x plus 1. Then I'm almost done, and I can write it as x plus 2, x minus 2, x plus 1. And again, what is nice about this form is that you can immediately tell for which x values this function is going to be 0. It's going to be for minus 2, for 2, and for minus 1. And you couldn't easily tell that if you would just look at this expression here. The last example that I would like to do here is a little bit more involved. Let me get some paper again. Here we go. So the last example is this one. Example. So let's consider f of x equals x to the power 3 plus 6x squared plus 11 times x plus 6. Now, for this polynomial, it is not very easy to see how we could write that in terms of factors. But what you can see, if you try, you can try and find a 0. So x is 0, well, it's going to give 6, so that doesn't work. If you plug in x equals 1, you get 1 plus 6 plus 11 plus 6. That's also not going to work. But if you try out a little bit, you see that f of minus 1 equals minus 1 plus 6 minus 11 plus 6. So we get 12 minus 12 equals 0. And then the theorem about factorization that we had tells you now, so factorization theorem tells you now that apparently f of x can be written as this x plus 1 factor times g of x, where g is also a polynomial of degree, and then one less. So our polynomial f has degree 3. So this is going to be a polynomial of degree 2. Now, if you would like to find this polynomial, there are different ways to do that. One is long division, but I'm not going to do it that way. I'm going to do it a little bit more systematic. And I'm going to say, well, g is a polynomial of degree 2. So what that means is I can write g of x as ax squared plus b times x plus c, because every polynomial of degree 2 has this form with some coefficients a, b, and c. And now what I'm going to do is I'm going to plug that in. So I'm going to take this expression and plug in here. So what do we find? X plus 1 times g of x. Well, that is going to be x times ax squared. So that's ax to the power of 3 plus bx squared plus c. And then the plus 1, so plus ax squared plus bx plus c. And I forgot to put an x here. So like this. And then I can take them together. So this is ax to the power 3 plus bx squared plus ax squared is a plus bx squared. Cx plus bx is b plus cx plus c. And now, apparently, we have this. So this is fx. This is x plus 1 times gx. And these expressions should be identical. They should be the same. So what that means in particular is that, for instance, this x to the power 3 that it says here should be the same as here. So what we find is that a equals 1. Then I can also look at 6 times x squared. And here we have a plus b times x squared. So apparently a plus b should equal 6. Then let's pick another color. Black always works well. 11 times x should be the same as b plus c times x. So b plus c should equal 11. And then finally, let's pick orange. 6 should be the same as c. So c equals 6. So what we have is that apparently a equals 1, c equals 6, and b I can find from either of these expressions. They're going to give the same, so I find that b should equal 5. So that means that we now have found the coefficients of g of x. And let me do that on a new slide. So what we find is that g of x is ax squared plus bx plus c. A we just found to be 1, so x squared, plus b we found it to be 5, so 5 times x, plus c, and c equal 6. And then f of x equals x plus 1 times g of x is x plus 1 times x squared plus 5x plus 6 is x plus 1 times x plus 2 times x plus 3. So much more involved, this example, but we have found now the factorization of the function, and we can immediately tell that our polynomial f is going to be 0 at -1, at -2, and at -3. Then the very last topic for this video is the intersection of functions. If you have two functions, y equals fx, y equals gx, and you're interested to find where they intersect, so these black dots, you would like to know for which x values this occurs, then you have to solve the equation fx equals gx. So let's do a simple example. And hopefully I can squeeze that here. Example. So say that we have fx equals x squared minus x minus 5. So that's a parabola. We have gx is x plus 3, straight line. And the question is, what are the points of intersection, or what are the x values at which they intersect? So what we do is we solve. So intersection points of the graphs, intersection points. We put fx equals gx. So we have x squared minus x minus 5 equals x plus 3. And together that gives x squared minus 2x minus 8 equals 0. And then if you do one more step, you will find, I'm not going to put it here because there is no space anymore, but for x equals 4 and x equals minus 2, you find that they intersect. So that's how you can do these types of problems. That brings me to the end of the video, so let's see what we have covered here. We have first introduced a function as a rule that assigns to each x in a certain collection, the domain of the function, precisely one value y, and then y belongs to the range of the function. We have looked at a couple of basis functions, polynomials, rational functions, and roots. And finally, we looked at finding the zeros of functions and factorizing a polynomial in terms of lower polynomials. That brings me to the end. I hope this was all clear. Let me know what you think, and I hope to see you in the next video.